All right. So let's talk about 5.3. 5.3 is about integration by substitution. This is going to be a very powerful tool for us when it comes to integration. We usually call this U substitution because U is the variable that we'll use to do our replacements with, to do our substitutions. But it doesn't have to be U. You could use T or W or whatever else, right? Anyway, but the idea is this, right? So the idea behind U substitution is to rewrite a difficult integral as a simpler but equivalent one. And U substitution works because of the chain rule. Okay, so let's just remind ourselves the chain rule. So let's say that the derivative of capital F is lowercase f. If that's the case, then what the chain rule says is that the derivative of capital F of g of x is lowercase f of g of x times g prime of x, right? So it's the derivative of the outer function times the derivative of the inner function. So rewriting the chain rule in integral form, in other words, if we were to integrate both sides of this, what we would get is that the integral of lowercase f of g of x times g prime of x dx would just be capital F of g of x, plus some constant c. So that kind of tells us that if we see an integral where we have some kind of inner function and then its derivative it just so happens to be sitting on the outside, then we can do a U substitution. We can let U equal this inner function. So the idea behind a U sub is that we let U equal this g of x thing. And then if that's the case, du dx is going to be g prime of x. Or in other words, writing that in differential form, we would say du equals g prime of x dx. And so that allows us to rewrite this whole big nasty thing. We replace g of x with u. We replace g prime of x dx with du. And so this just becomes f of u du, right? So it's much more simple. That's if you can. That's if it happens to have kind of this format, right? Now, unfortunately, there aren't really any hard and fast rules for choosing u. It's kind of something that you'll develop a taste for, I guess, with experience. But that is, if there's anything that kind of tells us what to let u equal, it's we want u to be whatever thing the derivative of is sitting outside here, right? So like if you notice that the derivative of something else is like sitting in with the problem, then you can usually let u be, that thing. It doesn't always quite work that way, but basically that's the driving force here, is that we're going to try to choose u so that we're replacing the g of x in the composition f of g of x. Now, one thing to keep in mind, if you're going to use a u substitution, then we have to completely eliminate the x. Okay. So what I want to do is walk you through. I think I've got 12 examples. I've got 12 examples of this because it's just something that takes some practice and some experience. So let's get to it. Let's walk through several examples. So let's evaluate some integrals. Let's do this. So first of all, to give you an idea of what I'm talking about, let's say that we had something like x squared plus 1 to the 50th power times 2x dx. Now, we could evaluate this integral by, first of all, multiplying this by itself 50 times. Now, that would take you probably, weeks. Maybe not quite that long, but it would take you a long time. Maybe it would take you weeks. Man, that would take forever. And then you'd end up with this really big, long, nasty problem. Actually, there is an easier way to do it that wouldn't take you weeks. If you know the what's it called? The binomial theorem. If you know that, then you could do this a little bit more quickly anyway. But it would still take quite a bit of time. But that's one way that you could do it. Now, another way that you could do it, though, is with a u substitution. You could say, well, notice that the derivative of x squared is 2x. So I could let u be x squared, but better yet, what if I let u be x squared plus 1? because the derivative of x squared plus 1 is also 2x, right? And by letting u replace this entire thing, then this entire integral is just going to collapse down to u to the 50th power, which is really easy to compute. So that's what I'm going to do. I'm going to say let u equal x squared plus 1, right? Then du equals 2x dx, right? In other words, du dx equals 2x, but I'm just sort of cutting to the chase and writing it in this differential form, du equals 2x dx. So this thing is du, okay, and this thing is u. So our original integral now becomes u to the 50th power du. And that's all there is to it, right? And that's really easy to integrate, right? We add 1 to the exponent and then divide by the new exponent. And add on our constant of integration, and that's it. Now, of course, we want to, we started with a problem that was given to us in x. So we want to give our answer in terms of x as well, but that's easy. U is just x squared plus 1, so now we replace the u with x squared plus 1. And that's the final answer. You can always check this by differentiating, right? If you take the derivative of this, you should end up back with x squared plus 1 to the 50th times 2x, right? Okay. So there's an example. Here's another example. Let's do integral of sine of x plus 9 dx. Now what's challenging about this particular integral is that we don't know what the antiderivative of sine of x plus 9 is. We know what the antiderivative of sine x is, right? Right? Derivative of cosine is negative sine. So derivative of negative cosine would be positive sine, right? So the antiderivative of sine is just negative cosine. But what about the antiderivative of sine of x plus 9? We don't know what that is. Fortunately, we can use a U substitution. We can say, if I let u equal x plus 9, the derivative of x plus 9 is just 1 dx, or in other words, just dx, right? So, so the derivative of this stuff is sitting right here. So I'm going to let u equal x plus 9, okay? Then du is just going to equal dx, right? Right, du dx would equal 1 plus 0, right? So du equals dx. Okay, and this integral now becomes sine u du. Well, that's easy, right? We just said what that was. That's just negative cosine u plus c. And then to get it back in terms of x, we just replace u with x plus 9, right? So it's negative cosine of x plus 9 plus c. And again, you can check all of these things by differentiating. So you're welcome to check this by differentiating if you'd like. Let's do another one. Let's integrate x minus 8 to the 23rd power. I'll let you pause the video and see if you can figure that one out. Okay, here's my solution. So, kind of same trick as before, right? I'm going to let u be x minus 8. Then du would be dx. And this integral would just become u to the 23rd du. So that's going to be u to the 24th over 24 plus c, or x minus 8 to the 24th over 24. Okay. Same sort of deal. Let's do cosine 5x dx. Okay. Now this one's maybe a little bit trickier, but it's not too bad. Okay, so again, I don't know. I know what the antiderivative of cosine is. It's just sine, right? But I don't know what the antiderivative of cosine 5x is, right? Antiderivative of cosine x, sine x. Antiderivative of cosine of 5x, don't know, right? But I can do a U substitution. I can let 5x be u. But now I have to be careful, right? Now du dx is going to equal 5, right? So du equals 5 dx. And that's kind of a problem because I don't have a 5 dx here. So what I can do is, you could think about this a couple of ways. One way to think about this is you could say, well, I can just put a 5 here as long as I multiply by a 1/5, right? And in fact, you can take all of these things out, really. You can call this 1/5 out here. And then there you go. There I've got du, right? So this is going to be cosine u du, as long as I have a 1/5 out there. That's one way that you could think about it. Another way that you could think about it is you could just solve this for dx. You could say, well, du equals 5 dx. That implies that dx equals du over 5. And then you can replace the dx with a du over 5. And the way you're going to deal with that then is to factor out the 1/5. And so you'll end up at the same place as what we ended up with here, right? So however you prefer to think about it is fine with me. I'll probably jump back and forth between those two different ways to think about it. But this integral now becomes 1/5 times the integral of cosine u du. And that's all there is to it. So that's 1/5 sine u plus c, or in other words, 1/5 sine of 5x plus c. And you can tell that that's going to work out when you differentiate, right? Because derivative sine is cosine, so we're going to have cosine x. We're going to have 1/5 times cosine 5x, and then times the derivative of the inner function, which would be 5. So it'll be 1/5 times cosine 5x times 5. The 5 and the 1/5 will cancel. You'll be left with cosine 5x, just like you started with, right? So it works out beautifully. Okay. Ooh, here's a good one. Okay, so this is a really good one. I don't think I have room on this page, so I'm going to flip the page. Okay, here's a really good one. Let's integrate sine squared x cosine x dx. Okay. There are a couple ways you might try to approach this problem. One thing that you could do, I don't know of any function whose derivative is sine squared times cosine, right? So I don't know what the antiderivative of this stuff is, and integrals don't distribute across multiplication. So you can't just say, well, it's the antiderivative of sine squared times the antiderivative of cosine. That's not exactly how it works, right? But what you could do is you could say, well, sine squared is 1 minus cosine squared, and then you could distribute the cosine and get cosine minus cosine cubed, right? The problem with that is that we know what the antiderivative of cosine is. We don't know what the antiderivative of cosine cubed is. So that creates some difficulties. But if I do a clever U substitution, I think this will actually work out pretty nicely, because notice, I can think of this, so I can kind of think of this like, alright, so this is sine x squared. This is just another way to write the same exact thing, but I think it's maybe a little bit more clear like this, because notice that we've got a composition here. You have something squared. Well, the something that you're squaring, if we call that u, derivative of u, right, would be, right, derivative of sine x is cosine x. So the derivative of this thing is sitting right here. So that tells me that I should let this be u. So I'm going to let u be sine x. Then du would be cosine x dx. Beautiful, right? And now this whole thing just becomes u squared and then du. Right? This thing is du. This thing is u. So you have u squared du. And that's all there is to it. So this becomes u cubed over 3 plus c. Or that would be sine cubed x over 3 plus c. Or you could call it 1/3 sine cubed x, whatever you like. But anyway, you could check that one and make sure it works out when you differentiate. But it should work out beautifully, right? In fact, it does. Okay, so there's that one. Here's another one. Let's do e to the square root of x divided by the square root of x dx. Ooh, okay. So this is the first one I've come across so far that I haven't really known what to do, just at first glance. And that's just because, like, I'm experienced at this, right? But this one I'm not sure. I'm not exactly sure. Oh, I think I've got it. Okay, so I think I've got it. I'm thinking, you know, I know what the antiderivative of e to the x is, but I don't know what the antiderivative of e to the square root of x is. So that kind of tells me, well, maybe if I let u be the square root of x. But then the only challenge is the derivative of the square root of x has to be sitting in the integral somewhere. And it just so happens to be, right? Because square root of x is x to the 1/2 power. The derivative of x to the 1/2 is going to be 1/2 times x to the negative 1/2. Well, x to the negative 1/2 is 1 over the square root of x, right? 1 over the square root of x. There it is, right? So the only thing we're missing is the constant 1/2. But I think we can do something similar to what we did in example D here, right? Do something clever like that. So let's get to it. I'm going to let u equal square root of x, right? Then du equals 1/2 x to the negative 1/2 dx. Or in other words, right, du is 1 over 2 root x dx. Okay, so here's what I can do. I can just force this to be 1 over 2 root x, right? Essentially what I've done is I've multiplied by 1/2, which I'm allowed to do as long as I balance it by multiplying by 2 there. And then I haven't changed anything, right? And now I've got 1 over 2 root x dx, right? This whole thing is du. And then this is just going to become e to the u. So this thing is du, and this thing is e to the u. So we get 2 times the integral of e to the u du. Antiderivative of e to the u is just e to the u. It doesn't change at all. And then rewriting this in terms of x, we're going to have 2e to the square root of x plus e. So as you can tell, you know, U substitutions make a lot of these complicated integrals really not too bad. Not bad at all, in fact. Okay, how many more do I have? I have 6 more. Okay, let's do another one. Let's do dx over 1/3 x minus 8 to the 5th power. Don't get too worried about this dx up in the numerator. This is just the same thing as 1 over this stuff times dx, right? It's just exactly the same thing. So don't get too nervous about that. Okay. Here's what I'm thinking about this one. So I'm kind of thinking of it like this: 1/3 x minus 8 to the negative 5 dx, right? And then I'm just going to let u be 1/3 x minus 8. And then du is going to be 1/3 dx. Okay. Now I don't have a 1/3 dx, I just have a dx, but I can force it to be 1/3, right? I can put a 1/3 here, as long as I put a 3 there. Okay. So then I've got du and I've got u. So this is going to become 3 times the integral of u to the -5 du. Okay. And that's that. So that's 3 u to the, you add 1 to the exponent, get -4, and then divide by the new exponent, right? Plus c. So that's -3/4 times u to the -4. U was 1/3 x minus 8. So it's 1/3 x minus 8 to the -4 plus c. And I'm happy with my answer like that. If you want to call it 1 over 1/3 x minus 8 to the +4, and then put that together with this denominator or whatever, I mean, you could do all that stuff, but I think you get the idea. Okay, let's look at another one. Ooh, okay. So let's do dx over 1 plus 3x squared. Okay. Okay. Well, if we let u equal the entire denominator, we're not going to have the derivative up here, because the derivative of the denominator is going to be 6x, right? Although that is a good problem. In fact, maybe I'll show you that one kind of as a bonus. But in fact, let's just do this. I'm going to call this h star. Right? This is just a bonus. If we had an x up here, then we could let u be 1 plus 3x squared. And so then we'd get du equals 6x dx. And up here I have an x dx. I can make it a 6x dx as long as I put a 1/6 out there. So then I've got du over u. So I would end up with 1/6 times the integral of du over u. Antiderivative of 1 over u is just ln of u, right? So this would be 1/6 times the ln of absolute value of u plus c, where u is just 1 plus 3x squared. So that would be not too bad. Right, that would be that one. But going back to our original problem, we didn't have an x up there. We just had dx over 1 plus 3x squared. What this reminds me a lot of is a tangent inverse, right? Derivative of tangent inverse is so remember dx of tangent inverse of x is 1 over 1 plus x squared, right? So that's kind of what this looks like. It's a 1 over 1 plus 3x squared. So the issue is that we've got this 3x squared. Okay, so that tells me maybe what I should do. Okay, so first of all, notice that this is the same thing as 1 plus root 3 times x squared. Okay, so that tells me that I should let u be the square root of 3 times x. Right? Because then I'm going to have 1 over 1 plus u squared, and it'll be just tangent inverse. So let u equal square root of 3 times x. Then du is going to be root 3 dx. So, alright, well, so I can force this to be a root 3 by putting a 1 over root 3 out here. And by the way, as we do this trick, it occurs to me that you might be tempted to do that with an x, right? You might be tempted to say, well, I can do this, and just end up with what I had up here. It doesn't work that way, okay? Because you're allowed to take constants out of the integral. You're not allowed to take variables out of the integral. So you can't do this trick with an x. You can only do it with numbers, okay? But okay, du equals root 3 dx. And so this integral becomes 1 over root 3 times the integral of, this is going to be replaced with du, and this is going to be 1 plus u squared. And there you have it, right? So this is 1 over root 3 times tangent inverse of u plus c. Well, that's 1 over root 3 times tangent inverse of u, which was root 3x, plus c. And there you go. So very different outcomes, right? Having an x there makes a pretty big difference in the outcome of what you get, right? Okay. Here's another one. Let's do 1 over x plus secant squared pi x dx. Okay, well, antiderivative of 1 over x is not a problem. That's just ln of x. Antiderivative of secant squared x isn't a problem. That would just be tangent x. But secant squared pi x, well, we don't really know, right? So that tells me that maybe I should let u equal pi x. Then du would equal pi dx. Now, when I go to replace all this stuff with u, I'm going to run into kind of a problem because remember, I need to completely eliminate all of my x's. So of course, this thing is going to be secant squared u. But what about this x right here? It might be useful for me to come back to this equation and say, well, this also implies that x is u over pi, right? So then 1 over x becomes 1 over u over pi plus secant squared u. Oh, and what do I do about this dx business? So du is pi dx. So I can put a pi here as long as I put a 1 over pi there. Alright? So then I'm going to have this is going to be replaced with du, but I need to have a 1 over pi. Come along for the ride. Okay. Alright, so this is kind of bothering me now. So I've got 1 over pi. I can put the pi up in the numerator. Pi over u plus secant squared u du. Okay. Pi over u. Well, goodness, I mean, I can take the pi out for this particular one. I know that antiderivative of 1 over u is just ln of u. So if I take the pi out of the integral, it would just be pi times ln of u, right? Okay, so this is going to be 1 over pi times pi ln u plus tangent u plus a constant. Okay? Okay. You can clean that up. I mean, if you distribute the 1 over pi, of course you just get ln of u plus 1 over pi tangent u plus c. And u you can replace with pi x, right? So this is ln of absolute value of pi x plus 1 over pi times tangent of pi x plus c. All right. Okay, let's do another one. How long have we been going? Man, we've just been hammering out example after example. We've been going for 30 minutes. We can do a few more. We can do a few more. Okay, we can do a few more before your attention span completely runs out. Let's see. So let's do integral of t to the 4th power times the cube root of 3 minus 5t to the 5th power dt. Okay. Well, this is a clear case where you've got the derivative. So here you've got an inside function. You take the derivative of that, you're going to get, something t to the 4th, which is sitting just right out here. Okay? So that tells me, let's let this stuff be u. Okay, so then du is going to be negative 25t to the 4th power dt. So I've got a t to the 4th power dt. I don't have a negative 25, but I can put one there, as long as I put a negative 1/25 out there to offset it. And so then this thing together with this thing is going to be replaced with du, right? And this thing is going to be replaced with u, and we're going to end up with negative 1/25 times the cube root of u du. Cube root of u is just u to the 1/3 power, right? So this is negative 1/25 integral u to the 1/3 du. Add 1 to the exponent, divide by that new exponent. Okay. I can flip and multiply, and I would get negative 3. U was really 3 minus 5t to the 5th. Okay, so it's a negative 3. It's a negative 3 u to the 4/3 divided by 4 times 25, which is 100. Okay, plus c. There you go. I shouldn't try to do so many steps. Some of you do a lot of steps in one step, and that's awesome. I guess I have an older brain than that. I don't know, or just I'm out of practice. But that's that. You should end up there. Okay, JK. Let's do integral of x squared times the square root of x minus 1 dx. Okay, this one's kind of challenging. Okay, if we let u be x minus 1, the derivative is just going to be du equals dx, right? It's just going to be dx. Well, then how do we get rid of this x squared? We could let u be the square root of x minus 1. And then, so I don't think this is going to work, but I just want to work it out. If we let u be square root of x minus 1, then du is 1/2 times x minus 1 to the negative. Yeah, that doesn't really work very well, does it? So we don't want to do that substitution. Letting u equal x squared isn't going to be very helpful because derivative of x squared is 2x, but you don't have a 2x. What you have is an x, but it's inside of the radicals, so that makes things challenging in terms of being able to do replacements with stuff very easily. So here's what I think we have to do. I think we have to let u be x minus 1, and then that means that x is u plus 1, and we'll just have to replace the x here with a u plus 1. Okay? So then du equals dx, and x equals u plus 1, right? So making my replacements then, I'm going to have integral of x squared, but remember you have to replace all of the x's with u, so it's going to be u plus 1 squared times the square root of u du. Now at first glance that may not seem very helpful, but notice that we can do u plus 1 squared pretty easily. That's going to be u squared plus 2u plus 1. And then we can distribute the square root of u, right? That's just u to the 1/2 power. And so we're going to add 1/2 to each of these exponents. And we're going to get 2 is 4/2. So 4/2 plus 1/2 is 5/2. We get u to the 5/2 plus 2u to the 1 plus 1/2 is 3/2 plus u to the 1/2 du. That's not bad at all now, because on each of these we can just use the power rule. So we add 1 to the exponent, divide by the new exponent. We're going to get u to the 7/2 over 7/2 plus 2u to the 5/2 over 5/2 plus u to the 3/2 over 3/2 plus our constant of integration. And we can clean this up a little bit. This is going to be 2u to the 7/2 over 7 plus, when I flip and multiply, this is going to be 4u to the 5/2 over 5 plus 2u to the 3/2 over 3 plus c. You can maybe find a common denominator or whatever if you want, but that's good enough for me. So that's that one. It does make me curious, like if we had gone back here and just distributed, so if you put the x squared inside the square root, it actually becomes an x to the 4th. And so we could have done this as square root of x to the 4th times x minus 1 dx, which would have been square root of x to the 5th minus x to the 4th dx. But that's still difficult, isn't it? Because you can't do a u substitution here. You don't have the derivative sitting on the outside. Yeah, so I don't think this is the way to go either. I think the way we did it is probably the best way. Okay, one more, and then I'll have some things to say. Some more things to say. But let's do, we actually secretly already did this one, but let's look at it again. Or if it wasn't this one exactly, it was something very similar to it. It was just kind of in disguise. Okay, so cosine cubed x dx. This is the same thing as cosine x quantity cubed, right? So you might be tempted to say, well, let's let u be cosine x. But then du would be negative sine x dx, and we don't have a negative sine x out here anywhere. So the good news is that with these trig functions, man, there's so many identities that you can use that are useful. And here's the trick here, right? So what I'm going to do is I'm going to call this cosine squared x times cosine x dx, okay? And then I'm going to use a Pythagorean identity for cosine squared. I'm going to call this 1 minus sine squared x times cosine x dx. Now, now I can do a U substitution, right? I can let U be sine x, and then du is going to be cosine x dx, right? So this thing gets replaced with du, and this is just u squared, so this is going to be 1 minus u squared. So I'm going to have 1 minus u squared du. All right, I can integrate that. This is going to be u minus u cubed over 3 plus c. And now I can just replace u with sine x. So that's sine x minus sine cubed x over 3 plus c. Isn't that interesting? So now, if you differentiate this, you should end up with just cosine cubed. Man, that's really crazy. That would be worthwhile, I think, as an exercise for you to check to make sure that that's correct. You might have to use some trig identities and stuff to get there, but I think it's correct. I think you'll get it. You'll get cosine x, and then here you'll get the 3 will cancel the 3. You'll get sine squared x. So you get cosine x minus sine squared x. Oh yeah, and then you make sine squared 1 minus cosine squared. Oh, but chain rule, right? So it'd actually be, you'd have another cosine x. Oh wow. Okay, so it would be cosine x. Here I am doing it now. Is going to be cosine x times sine squared x cosine x plus c. That'll do it, right? And then this will be 1 minus cosine squared. You get cosine x minus cosine cubed. This cosine, that cosine cancel. You'll just be left with the cosine cubed, like you should. Okay. All right. Goodness gracious. So I want to say something real quick about the inverse trig integrals. So we actually saw one already when we did part H together. We saw that this was like 1 over 1 plus something squared, and that's like a tangent inverse format. So generally we can say this about the inverse trig functions, right? So anytime you see something of the form 1 over something squared plus u squared, well, that's just going to be 1 over the something times tangent inverse of u over the something, right? For sine inverse, it's going to have the square root of something minus u squared. And for secant inverse, it's going to be 1 over u times the square root of u minus the something. So notice the order of subtraction, right? The order of subtraction matters. Also, this is not a typo, right? These two have a 1 over a on the outside. Sine inverse does not have a 1 over a on the outside, and that's how it's supposed to be written. And I'll prove the tangent one, the tangent case, and I'll let you prove the other two on your own if you're interested. But they're similar proofs. It's just a U substitution, right? So here's how it works, right? So integral of dx over a squared plus x squared. Well, first of all, you can factor out an a squared from the denominator, and if you do that, you would be left with 1 plus x squared over a squared. Well, x squared over a squared is just x over a quantity squared, right? Okay, so this is what you get when you factor out an a squared from the denominator. Now you can take that entire 1 over a squared out of the integral, and you end up with dx over 1 plus x over a quantity squared. Now we do the u substitution. We let u be x over a. So then du is going to be dx over a. Okay, so if I solve for dx, I can say a times du equals dx. So I'm going to replace the dx with a du. I'm going to replace the x over a with u. and the 1 over a squared comes along for the right. So this is where I end up. Now this a and one of those a's will cancel, and you'll just be left with 1 over a. So you'll be left with 1 over a times the integral of du over 1 plus u squared. And this is just tangent inverse of u, right? The integral of 1 over 1 plus u squared is just tangent inverse of u. So that's that, right? The good news is that now we can use these shortcuts, okay? So we don't have to go through this process over and over and over again. So let me just give you one example of that, and then we'll call this section good. I'm going to try to squeeze it in here. So let's do dx over square root of 2 minus x squared. Okay, so this is a sine inverse format. I know that because for one thing I don't have an x on the outside of the square root, and for another thing I'm doing the subtraction as number minus variable rather than variable minus number, right? So this is a sine inverse format. So following my my little shortcuts, I know that this is just going to be sine inverse of u, which in this case is just x, over a, which in this case is going to be square root of 2, right? Because the format is a squared minus u squared. So a squared is 2. That means a is square root of 2. So this is x over square root of 2 plus c. And that's all there is to it. Okay. All right. So a bunch of examples. Hopefully you have the idea. That's all I'm going to say for now.